So we're now transitioning our focus from an overview of threads to a focus on Java synchronizers. We will talk at length about Java synchronizers shortly. But before we get there, I need to give you the overview of the Java memory model, because everything in Java that relates to synchronizers depends on an understanding of its memory model. So you're going to be aware of the Java memory model as the objective from this part of the lesson. Maybe you should see beware of the Java memory model. That may be a better way to say it. So what is Java's memory model? Well, first of all, you can learn about Java's memory model in several places. This is one place to go. This is a website from my good friend and colleague, Doug Lee, who is a professor at State University of New York, Oswego campus, SUNY Oswego, and he wrote most of the Java concurrency libraries that we use. So great guy, really interesting. Whenever I get flummoxed with incredibly obscure issues in Java concurrency, I give him a call and he sets me straight. So Java's memory model defines the semantics of memory shared by multiple threads within the context of a Java process. And we'll see why this is important. It's very, very, very important now with modern multi-core processors. So here are some of the things that the memory model defines. It defines what instruction reorderings are allowed in memory. If you recall when we talked about sequential programming at the very beginning of the course, I mentioned how sequential programs give the impression that the statements execute one at a time in the order that they occur in the code. The textual order is the order of execution. And then I said, well, that's not quite true under the hood when we look at things like the pipeline out-of-order operations that you can get in a modern processor or with a modern assembler. It can rearrange the instructions. Under the hood, you never do this yourself. It does it as long as it obeys certain semantics and certain properties. These are the types of properties it has to obey with respect, especially to memory management. And there's a bunch of things that can reorder instructions at various levels. The Java compiler could do it. The just-in-time compiler could do it. Processor instruction pipelines, the assembler, the caches, you can reorder things all over the place. And there's a bunch of subtle issues here that you have to be concerned with. So here's one of them. So let's assume that we have two threads, thread 1, thread 2, and we have a couple of fields that those threads have access to in some sort of quasi-global thing, and they have access to X and Y as fields, and they're set to the value 0 initially. Okay, so far so good. So a question that arises is, what are the semantics of these fields with respect to those threads? So to make the example more tangible, let's walk through it. So here's thread 1 and thread 2. They both start up. Thread 1 sets the value of the global variable X to 1. Thread 2 sets the value of this global field Y to 1. So now X and Y are set to 1. And then thread 1 is going to assign some local field or some local variable J the value of Y, which has been set to 1 over here. And likewise, thread 2 is going to set the value of I, which is a local field or a local value, to X, which was set over here. And the question is, what are the values of J and I? And the answer is, according to the Java memory model, it's really non-deterministic at this level because there's no locks involved here, there's no synchronizers. So it could very well be the case that J would be set to 0, even though it was set to 1 in this other thread before this assignment occurred. And likewise, I could be set to 0, even though it occurred after X was set to 1 in this thread. And the Java memory model says that is okay. There's nothing wrong with doing that. And the reason it does that is to ensure that there's all kinds of opportunities for hardware optimizations. We don't want to have what's called a strongly ordered memory model, which would force incredibly sequential operations in our system. That would be bad. So instead, we have a weakly ordered model, which allows for hardware optimization. So you can read more about memory ordering and hardware optimizations at this link. Another question is, what are the outputs that can occur in a correct Java implementation? And again, you can read about this. This is the Java memory model specification. You can read about that there. So let's take a look at this example. So there needs to be some control of the values that you can see. If we have a situation where we do like we did before, we have X and Y equal to 0, we start threads, we assign some local variable r to x and local variable r1 to x, r2 to y. And then we go ahead and do these assignments down here. You don't want the results just to be random gobbledygook. They have to be based on something. So you don't want, the memory model is not so generous and so lax that it'll just let anything happen. But without putting in synchronizers explicitly, things that happen may not be expected. It may be a surprise. Now, the thing to remember about this is reading the Java memory model, like reading the specification or the frequently asked questions, is really, really, really boring. So the good news is, if you learn how to use the synchronizers we're going to be talking about here, which include mutual exclusion, locks, includes coordination mechanisms, includes atomic operations, and includes barrier synchronizers, all the things I show here as memes or visual depictions on this slide, then you pretty much don't have to care what Java's memory model spec says, because it will protect you from all of the vagaries and optimizations and weak ordering semantics and so on that it will define out of the box. And instead, you can work on writing your code and learning about these synchronizers. So that's a good thing. So that's the end of a quick overview of Java memory model. That's mostly there just for completeness. You won't really be expected to know much about the Java memory model other than to know that without putting in synchronizers, having multiple threads run and access unprotected shared mutable state or shared mutable data is the root of all evil in concurrent programs.